And Genie.
circuit.
Oh, sir, still asleep?
You're still on the ball now. Just forget right now. Push the ladder. What is talk about the four now? Right? What is talk about the four now? Let's start
Okay. Okay, I'm here. Okay, I'm the host now.
Yes, sir.
All right, thank you. So, see if I can. Full screen it, right? And
Sir, remember when you're ready to record here, sir.
right. I have recorded the other ones, you know. I'm not sure whether I've pasted them because I think I have a upper limit of 500 megabytes and they're all about 50. That only give me about 10 recordings. But what I can do is put them on, and then if I run out of space, I delete the early ones and continue adding. I've never tried that, but I think it will work. Right. Oh, okay. So we have 34 on already. All right, well, we won't waste any more time then. And good afternoon, everybody. And let me bring this one up. Right. Before I start recording, then I will just go through my little preamble. And I see we're running a couple of weeks behind, actually. We should be looking at somewhere at the discrete Fourier transform. We haven't got there yet. But we'll catch up all right. So we really started off, we're still doing the sort of review, but coming more into the nitty-gritty then of DSP. So the first thing we did, of course, is look at our signals and how we represent our signals. And then we're looking at the systems part of it. And today I want to finish going through the systems, and I want to be able to run through convolution, because convolution, of course, you will know that convolution is a process where when you input a discrete time signal into a discrete time system, convolution is what takes place between the system and the signal, and you obtain your output. And so once we have done that, and we'll mention a few other things as we go along. So once we have done that now, we can start actually looking at a few more interesting things. I hope you will find them interesting I always think that the first part here is a bit boring, but we can get into the more interesting stuff right away. All right, let me just admit. Okay, so we're going to continue with discrete time systems, and our objective then, thing not going to work with okay, yeah. Right, so I have to review the following topics. We should know something about them already. The linear time invariant systems that we are going to be working with in this DSP course are these here, shown here. And, you know, I think we have gone back too far. I think I am right. All right, so I'm going to shut down this one here. Is the second part I am supposed to be doing. So let me go and get that. I hope I can find it all right.
Good afternoon, Mr. Someone's waiting to be waiting.
Someone is waiting. All right. All right. They won't miss anything. Let me find all right, hold on. I'm just gonna stop share here. See, okay. Find my way. Is anybody hearing me?
Yes, sir.
Yeah.
Yes, sir.
So
What are you hearing?
I'm not able to get this thing back up. Yeah. Okay. Oh boy. So we can full screen, share screen. All right, this is where I want to be anyway. So, okay, so we're part 2. So the one I started just a while ago is what we did last week. So here we go. All right, so the main thing we want to do is look at the main types of filter structure, finite impulse response and infinite impulse response. And we want to also look at the realization of these filters in the block diagram form. So I'm going to start the recording now. Right, so just to recap from the first slide last week. So our discrete time system is, the function is to process an input sequence and in turn generate an output sequence. The discrete time systems that we will be looking at will be single input, single output systems. And that's normal for undergraduate course. All right, so we're going to start then by looking at a simple filter, which is a moving average filter. And averaging is commonly used where values fluctuate randomly. By smoothing the values, we can use it to show trends more clearly. It's used, for example, in things like stock markets. I understand it's very widely used for stocks. So the general equation for a moving average system is shown here.
Remember, we need to determine RD and R. So, what we need to do first? With the moments, what we need to free body diagram. So we need to draw. It's basically the same thing, but not.
Thank you. Right. So here is our equation written in mathematics, right? And really all this is saying here is that if you're going to use 3 values in your filter, then it's 1 over 3. So m is the number of values, and going from k equal 0 to m minus 1. So from 0 to 2, it's x of n minus k. In other words, if we write it out, we see this is the equation of our system. It's 1/3 x of n plus x of n minus 1 plus x of n minus 2. So we're taking 3 values and we're averaging in. So we're going to add them and divide by 3. Right. So here we're going to look at an example using a sequence 2, 4, 6, 4, 2. And I plugged them into a table. So this is a very useful form when we're going to be calculating things, is to make a table of it. And here's how it works. So, I'm actually starting at n equal minus 1, 0, 1, 2, 3, 4, 5, 6, 7. Although we only have 5 values here, there are reasons why I've chosen to do this. We would normally start at 0, right? So our first value is starting at 0. So our input values, x of n, are 2, 4, 6, 4, 2, and then all the rest we consider zeros. All right, because we're just going to take a very short set of input values here, as shown here. In the next case now, the next step forward is that we will already have one pass value here, which is 0 now, and then our 24642, and we step through. Okay, so our output y of n is just going to be the sum of these values here, x of n, x minus 1, n minus 2, and divided by 3. So here, 2 divided by 3, 4 plus 2 divided by 3 gives us that, and so on. And I will just move on. So here is our output now. Yn is equal to 2/3, 2, 4, 14/3, and so on. So, easiest way to evaluate what this has done to our input signal is to plot them. So, sorry. So, in the blue, I have plotted our input signal x of n, and in the brown is the output signal y of n. So what we see that is basically it has smoothed out our input signal a bit. A good exercise would be to run it with some really random values, and there are places on the internet you can get random values, you can get the stock values, you can get sunspot values and so on, and average them out. And, you know, like sunspot activity varies very much from year to year, but there is actually they say a 10-year cycle. So if you look at the values from year to year, you probably won't be able to make much of it. But once they run it through the filter, averaging filter, and look at it, then it's much easier to see the 10-year cycle. Unfortunately, it doesn't work with Lotto, so don't need to waste your time trying it on Lotto. Okay, so this moving average filter then is an example of the subclass of filters known as finite impulse response. In other words, these filters just have a finite set of coefficients, set of values, and therefore your input, as long as your input signal is finite, your output signal will be finite. So these are the finite impulse response filters. And the other thing to note with these filters, if the input is a delta function, delta n, then the output will be the same as the characteristic of the filter. In other words, it is referred to, what we get out is referred to as the impulse response of the filter. Right, so the filter that we just described in mathematical terms then is shown here, and using our block form, or schematic form then if you want. So here's your input signal, and these here are the gains going through. So in this case here, very simple. It was 1/3 of x of n. So when x of n came in here, we had 1/3 x of n here. And when we follow it through here, it has been delayed. So we have 1/3 x of n minus 1 coming here, and the final term, 1/3 x of n minus 2 comes through here. And then they're all added together. So we get 1/3 at the output, 1/3 x of n plus 1/3 x of n minus 1 plus 1/3 x of n minus 2 gives us our y of n. So for the equation that we looked at just now, the moving average, then this is our realization of that filter. Right, and in fact, you can actually plot this filter in terms of its frequency and phase response. I took the liberty of doing it with Matlab, and here is our plot in Matlab. All right, now, what it's really doing is that it's taking a digital filter and it's plotting it, plotting the frequency response as an analog signal. So here is the frequency response, and here is your phase response. In other words, when that signal comes in, at one frequency there will be, at 0 hertz, there will be 0 phase shift, right? At 0 hertz, there will be 0 attenuation of that signal as it goes through. But as our signal increases in frequency, then we see that our signal becomes attenuated till at some point it goes right down to 0. Now, we notice that it goes back up again, but I will say a bit more about that in a minute. It's always good to talk about filters early because this is going to be a heavy part of the course. And in terms of the phase, we see that there is a phase shift going as your frequency increases. There's a phase shift of your signal going through the filter. And even a very simple filter like that has that effect. If we put a signal through it, we get a phase shift. At this point here, there is what is known as a discontinuity, really. It's shown that there's a discontinuity at this point here in phase, and it goes from being phase shift going from one direction, and it goes right over into the other phase angle then. But we're not really interested in this right now. Before I move on, what I just want to point out, I took the liberty of putting this green line in here, because some people would look at this and they would immediately say, oh yeah, this is not a low pass filter. Notice that it is a low pass filter based on this curve going around here. But then they say, but then signal begins to go through again. Yes, sure it does. But a filter, the band pass of a filter is between 0 dB and -3 dB. So I've estimated where -3 dB is and put a little green line there. It doesn't really matter. But we clearly see that if this is -20 dB, -10 is somewhere around here. And so on the side of the curve, it never gets to anywhere above -10. And therefore, this part of the curve is still out of band, out of the pass band. So your pass band for your filter is really from 0 up to about this point here, which is probably about 0.3 radians per sample, right? 0.3 pi. Okay, so all of this will be a bit confusing at first, perhaps. Here we have our normalized frequency, right? And it's normalized to pi radians per sample. So we'll talk about that a bit more later on. But for now, it's just to show you that our band pass filter, our filter is a low pass filter, sorry. Right, so it's just saying then that even this simple, even a simple filter structure like this is actually a working filter, workable filter, usable filter then. Let me put it that way. All right, so we have introduced now the FIR filter, finite impulse response filter. So we say a bit more about that. Our filter then, FIR filter, has a limited number of coefficients. So we have here our equation of the general form of FIR filter. And we notice here our output then from our FIR filter will be a limited number of values. So it's going to go from k to n minus 1. If it wasn't a limited number of values, then this value here would be going away to infinity. Our b of k, and again, I'm introducing terminology which is standard terminology, but it doesn't have to be used. It's like, it's not written into law, but it's a standard terminology. So here, these are known as your B coefficients, and we'll understand a bit more about our B coefficients in a minute. And here, our input values. Right, so the BK are known as the coefficients of the filter, and this is specifically a FIR filter. So knowing these B coefficients here will completely define our filter. So for example, if we had a filter with the B coefficients being 3, minus 1, 2, 1, we would know that we have a filter, length 4 filter, such that y of n is equal, and so on. So for a bit of practice, if you're wanting to do it, going through again the note later, you can use this now and you can draw your filter in terms of its components. So where are the delays? What are the delays? What are the coefficients, the gains, and what the summation will do? In this case, we have a minus. Here we have 2 pluses. All right. So the general form of a FIR filter is shown here. So your FIR filter only has B coefficients, and it only has feed-forward paths, what are known as feed-forward paths. So each of this is a forward path, and so on. And as many coefficients as you have, right, I've shown here 1, 2, 0, 1, 2, and then down to B of n, and then to B of n minus, B of n minus 1, B of n. So all of these now are your feed-forward paths. These are your forward coefficients, or your B coefficients. And your FIR filter is of this structure. All right, so characteristics then of FIR filters, they are stable. They contain only feed-forward paths, as I said. And you can obtain the impulse response by plotting the output when the input is delta n. Now, the good thing about them, of course, is the stability. Bad thing is that they are inefficient in the use of memory. They're actually very wasteful of memory, and memory in the hardware design of DSP chips and so on is very valuable component. That's fast memory. And finally, they can introduce long processing delays. All right. I don't know how this came here because this is not an IIR filter. Sorry about this. What is going on? I think, yeah, sorry, that's the same slide just got repeated. Right, so we've said that all we really need to say about IIR filters right now, FIR filters right now. Let's quickly look at the IIR filters. So to help us understand why is an IIR filter needed? So we look first then, consider the filter defined as follows. Our H of n is 2, 3, 4, 5, 2, 3, 4, 5, 2, 3, 4, 5, going on forever and ever. We'll think of it as an infinite impulse response filter here. But these are all the coefficients of the forward pass, right? And we notice that the coefficients are periodic. So 2, 3, 4, 5, it repeats every four coefficients. So if we take our h of n here and we shift it, and we're going to shift it to the right, we're going to delay it. Delay by 4 means shifting to the right by 4. So we're delaying our h of n by 4. So now we have 0, 0, 0, 0, and 2, 3, 4, 5, 2, 3, 4, 5, 2, 3, 4, 5. That goes on to infinity. So could we actually build this filter? No, we couldn't build this filter, not as it stands right now. How can we realize this filter then? Well, if we subtract our delayed coefficients from our undelayed coefficients here, we see we have h of n minus h of n minus 4. We've shifted this. We subtract that from that, that from that, that from that. When we get here, so we subtract these and we get 2, 3, 4, 5. When we get here, we're subtracting 2 from 2 is 0, and so on all the way along. So what happens from this point on is that our coefficients are 0. Therefore, we don't need to have any physical component for it. All right, we don't have to have any more delays or gains. So when we have done this now, we're left with a sequence 2, 3, 4, 5, which is our shifted set of coefficients. So I just brought this over from the previous slide just to keep reminding us. So here's a little funny part. When I say funny, it's going to be a bit difficult to understand at first off, but look through it a couple of times. So if we rewrite now our equation for our h of n now, we see that we're going to, instead of using the arrow to indicate our n equals 0 value, we'll just use our delta n. So we can rewrite now our equation in a more mathematically acceptable form, where the left-hand side is determined by this. So 2 delta n plus 3 delta n minus 1, 4 delta n minus 2 plus 5 delta n minus 3. So here now, this part here is representing this part. And then I remind you that I had said one very useful function about our delta function is that when you input your delta function to a filter, what comes out is really so your output y of n is what your impulse response is. So it means then, if you will substitute x of n for delta n, or in this really it's delta n for x of n, then you can substitute y of n for h of n. Right? So think around that a bit. So what we're saying and what is acceptable in DSP, when you substitute delta n for x of n, you substitute y of n for h of n. So substituting into this equation now, substituting for h of n, you're going to substitute y of n. So this becomes y of n there minus y of n minus 4, and you substitute x of n, right, where you see delta n, you have 2x of n plus 3x of n minus 1 plus 4x of n minus 2, and so on, right? So now what you have here is the difference equation relating the output y to the input x. And again, here I put it. Now, since we really always want to make our output as a subject of our equation, right? So we really are just interested in our y of n. So we rewrite this equation and we bring our minus y of n over to the right. So our difference equation is now as it's shown here, with our y of n minus 4 over with our x's. Now, just to remind you, since our h of n was infinite, yes, then the system response would also be infinite. Hence, this system now, sorry, coming. So that the system remains an Iir filter. But now we have a new structure. And what is the new structure? Here is the new structure. So we still have our input signal coming through here. This is still 2x of n, or b0 was 2, 2, 3, 4, 5. So our, at this point here, we still have x of n, 2x of n plus 3x of n minus 1 plus 4x of n minus 2 plus 5x of n minus 3. And then we have our y of n now. So we took our y of n minus 4 and we so our y, we delay it 4 times. Notice I have a minus 4 there, and then we multiply it by our coefficient. And in this case here, the minus might not be correct because we have plus y of n minus 4. Plus y of n minus 4, yeah. So in fact, this would just be 1, or it could be a straight piece of wire. And then, right, so this 4 is not correct. We'll correct that. But note that this 4 here should just be 1. Right, so this now here is what? Is a feedback path. So our Iir filters have feedback paths. So these are the feed forward, these are the feedback paths on the right. However, it still goes through and out there. Now, a lot of people might say, but hold on, I don't really understand what is going on here. How do I, why is it I don't have a loop here? So what is there keep going round and round and round. But remember, these things are discrete time. They're stepping through. So when you step through here, it no longer can go back around. It's not a continuous thing. it happens only at periods of time. So when you get this value coming here, it is only there till the next period of time. And then at the next period of time now, you have another set of calculations. So it's not a case where you can have, say, a loop, and that's why it can be unstable. All right. However, IIR filters may be unstable. They have stability problems, and we will look at that further down the line and see how we deal with the stability problems, how to evaluate the system so it will show us whether it is stable or unstable, and so on. It has feedback paths as well as feed forward, and but they are efficient in the use of memory. They're referred to as recursive filters, and I think there are one or two other things, I just haven't put them in. Okay, I'm going to take a break in a few minutes, but before we leave the topic here, I want to talk about the difference equations. Now, I'm sure that you've had your fill of differential equations in continuous time systems. And we're going to, so we'll look at the difference equations in discrete time systems. They are an important subclass of linear time invariant systems, where the output and the input are related by an nth order linear constant coefficient difference equation. And here is a general expression then. So the y terms, all the y terms on the left, and all the x terms on the right. It's one way of writing it, a standard way. And you have your A coefficients on the feedback path, you have your B coefficients on the feed forward path, and it can be written in the expression as shown there. However, really most of the time it's desirable just to express the output as a subject, the output on its own, because expressing it in this form here doesn't give you a good picture of what y consists of. So it is very often desirable to express. To express it in terms of y. So we can bring y, of course, if k is 0, we have a 0, y of n, right? And we want to take that out and keep it separate. Then you may have all the other terms. So you can bring all from k equal 1 through to n. Those terms can be brought over onto the right, and therefore what we have is our expression here, where our output y of n, as I said, if this term here when n is equal to 0, we have a of 0, so we have 1 over a 0, and then having brought all these terms over to the right, we can put them inside a bracket, because when we divide through, if we're going to divide through this by a of 0, we also have to divide through that by a of 0. and therefore A of 0 is outside of the bracket, and then our negative values, our terms which came over and became negative are here. So here are the balance of our y terms from k now equal 1 to n, and these are them. And unfortunately, I can't see at the bottom because this thing is in the way. I know I can remove it. Anyway, and then here are our feed forward terms going from little m up to big M.
Excuse me, sir.
Yeah.
Could you just explain again how you got the 1 over A naught?
Okay. Yeah, I should really have perhaps tried writing out the first couple of terms. But if we were to if we expand, we can expand the left and the right summations, right? So if we expand both of them, but we get, of course, A0 y of n plus A1 y of n minus 1 plus A2 y of n minus 2 and so on, going right up to n. And if we expand on the right-hand side, of course, we get B0 x of n plus B1 x of n minus 1 and so on. As we saw a little previously, as we would see here. So here we would see, because our B0 was 2, so we get B0 x of n plus B1 x of n minus 1, and so on. So, but in the general form, of course, we're just expanding all of these. All right, now, of course, we're going to take all the other terms over, all the other A terms. So we're going to take over A1 yn minus 1. We're going to bring them over to the right-hand side. So this is where they are. And of course, we're going to...
Okay, sir. I'm seeing it.
You're seeing it now?
Yes, sir. Yeah.
Right.
Took out the first term, the 0 terms.
Right. What we would have been left with over on the left-hand side would be A0 y of n. So we just divide through now both left and right by A0. And that's why we get our 1 over A0.
Yes, sir. I'm seeing that now. Thank you.
Good. Oh, yeah. I mean, everybody feel free to question, you know. All right. All right. So this brings us to the end of this little section. So what we're going to do next, of course, is that, so we have sort of defined what our systems look like and how we can represent them. And then, so the next step now is to look at how do we calculate the output of a discrete time system given a discrete time input. And of course, you'd appreciate that it involves convolution. And you would also appreciate that convolution in the continuous time domain is well, for me, I don't know if anybody has the same dislike to it, but requires a lot of integration and so on.
Yes, sir.
Convolution in the discrete time domain, and if you have already done it, you will, as I think sometime that it's in the signals and systems. But anyway, we'll go through it again. And
sir, it involves a lot of repetition of integration, like looking at if.
Sorry.
Well, I was asking if it includes a lot of like integration by parts and stuff like that in the continuous time domain. Just trying to make a connection is all.
Right. In the continuous time, yes. It involves integration, which you can do in parts. Certainly you can break up some signals if you have a ramp followed by a square wave, or if you have a square wave, you can reduce the limits, get rid of, or if you have a square pulse and so on. I mean, with me, all that thing is fading into the distant past. I didn't like continuous time systems. But the time system is lovely. I really enjoy it, So what we'll do here, could take a 5-minute break, and then what we will do is we'll look at convolution. So that's it. Join back about 4:15 then. All right.
Sir, when you say 4:15, you mean in a minute, sir?
Oh, I'm looking at a clock, which I think is slow. All right, in about 20 past then. John, yeah, because I wouldn't mind a 5-minute break from my throat. So yeah,
Okay,
about 20 past then. Oh yeah, this is, that clock is about 3 minutes slow then. I just took in a break.
Assalamu alaikum. Alaikum assalam.
Okay. Right, we're going to have a look at convolution now. Let's see, I still have 37. Good. As I mentioned before, and as you should know, that convolution is the operation then that is gone through when an input signal is passing through a system. In most systems, then convolution takes place. A perfectly linear system with just a single value of input, a single frequency, and so on. You may not need to do a convolution operation. You can do a simple scalar operation. But particularly where there are other circuit elements, and in the case of discrete time systems, those are delays, then you have to take into account, you know, what went through before, perhaps. Right, I haven't started, so I'm going to start recording now. So now we look at convolution. Right, and we title it as the response of a linear time invariant system to an input sequence, specifically discrete time convolution. Now, the derivation of the convolution sum, I'm just going to go through briefly. First of all, we know that a discrete time linear time invariant system will present a response to a delta impulse function as shown here, and we know that inputting our delta function to the system, and we term the response of the system h of n, will give an output y of n, but it so happens that if we go through, we will see that our output y of n is actually the same as h of n. That is a response to a delta function. It happens in continuous time signals as well, except that in discrete time systems, we can very easily generate our delta functions. In continuous time systems, it's not really feasible. I've seen on the internet, I saw where these people were using a gunshot to simulate a delta function. It may be the closest that we can get. I don't know. But in discrete time, it's much easier. So if we input our delta n to our system here, our output is the same as the system response. So then we can look and say, if we delayed the input of that signal by k, then the only difference to the output is a delay. So the response of the system to delta n minus k is simply h of n minus k. So that is the time invariance property of the system. The other main property, of course, that we're interested in is the linearity property. So we know that if we multiply our input signal, and here we will use delta n minus k, if we multiply it by a value which is x of k, then that is the coefficient, then our output will only have a gain of x of k. So here we say that if we input a signal x of k, h of n minus k, then we expect to get out our response should be x of k h of n minus k. So we showed previously that any sequence x of n could be represented as the sum of individual scale delta functions, so that we could express our signal xn here as a sum of our coefficients x of k multiplied by delta n minus k. In other words, this is what gives our time marking. So we know that when n minus k is 0, then the kth value of the sequence is what is going to be our x of k. Right. So here's our input signal expressed. And therefore, if we use the second linearity property, that is superposition, then what we can do is that what we're actually doing is taking the whole set of times, possible times from minus infinity to plus infinity or just infinity. And we're taking the individual responses at each of those times and summing them, because that of course is superposition. So we are now summing each individual operation to give us this function here. So notice you could also say, well, here, since I input delta n minus k, then I can substitute it. If I substitute, then I have here h of n minus k. So our h of n minus k is all the individual responses put together, summed together. That is your superposition. And therefore, the output at any given point in time here, or nth value of the output, is determined by this equation here. And of course, it is a sum from minus infinity to plus infinity of all the individual operations that went on in that system. But that is convolution. So, given the impulse response of any digital system, it is possible then to compute the discrete response due to any input signal x of n. Right, now, good, I hope we understand that. And so the next question is now, how do we do this calculation? This is quite a difficult looking calculation. So before we start doing that, then we're just going to say that this, of course, is convolution or the convolution sum. In mathematical terms, it is written in this form here. In Matlab, of course, we can't use this expression here because that means multiply. But in Matlab, you just simply write CONV. Right, so our convolution sum is just written in shorthand like that. And the summation really has a simple graphical interpretation, right? Because if we go back here, what we see that here is that we have a set of terms here which k is going from minus infinity to plus infinity then. And we see we have here minus k. So first thing you would want to do then is flip all those values as it says here. All right. So the first, you could plot h of k and then the flipped and shift values of x of n minus k, right? Where of course n is fixed, and then you go through all this rigmarole and all that. But I don't think you can. The best thing is go through a couple of convolution demos. There's this one from Johns Hopkins University, now very well known because of the COVID counting that they are doing, and so on. So you can visit these sites. I hope they are still valid. I hope they still work. But we won't try and do that on the slideshow here. We're going to look at some other methods. Right, so the first one I will mention, I don't think I'll bother going through it. I call the Lti form. So what you basically are going to do, you're going to take a system with the impulse response shown here, very, very short, very simple, and you're going to take another sequence and xn here, which is shown here. This is our zeroth position here, and there is 1. And you're going to try and plug in these sequences into this operation. Well, it's just meant to show how tricky all this can be. How tricky all this can be, because here you're going to have to determine what is the range of values of k. So k is going to go from right, so you want to plot here, k is going to go like from -1, 0, 1, 2. And then you also have to take into account your h of n minus k. So when k is -1 and n is 0, what are the limits and so on? Not very easy, very confusing. But you could take them and you could work them out one by one. So you go in k x of -1, so on, so on. So work it out and you get that. Then for n is equal that, work it out and you get 3.5, and so on. So, well, the output sequence then should be 1, 3.5, 4.25, and so on, with your 0th value being this 3.5. Fair enough. I wouldn't try and do it for anything more than these. So, a simple sequence like this and this. Not very nice at all. So, are there other methods? Of course, there are other methods. So, you can read through the notes. The one I like to do, if you have to do it by hand, is called the convolution table. And the convolution table then is just going to say that you can put all your values into a particular table and calculate them and read off the values diagonally. It's shown here. So I'm hoping that I have put in the value. All right. So what would be good is, you know, if I thought I had an example here. All right, so for example, you're going to take here you have 1, 2, 3, 4, 5 values of x. Is this what we had before? We had one, 2, 3, 4. I think we have 5 values of x. So x is 2, 1, 1.5, 0.5, and let me just get rid of this thing. Right. Okay. No. 1, 2, 3, 4. All right. So we don't have a set of values to plug into this. I will just explain it to you, and we can do it at another time. Okay. So basically, you're going to put your table is going to be drawn like this: rows and columns. In the columns, you're going to put. You can either put your x values. X0, 1, 2, 3, and 4, and so on. So you could put your actual values in there. Let us say 2, 1, 1.5, 2.5, and 0, for example. And you put in the column here so you're going to put in your rows now. At the head of the row is going to be your h values. If these are the x, these would be the h. Right? So you put in your h values. Let's say 9 minus 3, 7. You put them in there. And then you take now where each row here and column intersect, you will multiply the values at the head. So where this was, what was it, 3 or something. Supposing it was 3 and this is 2, so you multiply 3 by 2 and that gives you 6, you put it there. Here, 3 by 1.5, 4.5, and you put it there and so on. And you fill out this table. And then simply to find your values, you simply take the diagonal values and you add them. Now always first here, that value will just be one value, right? And the same for down here, always just one value. So the first value you would take and you put there, that is your y0. Then here you will have 2 values, you add them algebraically, of course. If one is minus and one is plus, then you're adding them algebraically and you put the result here and so on. And you go through and you do all the calculations and you add them diagonally, and what you are left with here is your output sequence. It's very easy to do. Of course, that's assuming you're just dealing with integers, or so you can do it in your head. But that is how you would want to do it if you were given, say, in an exam, you might be asked to do the convolution between an input sequence, 5 or 6 values, and a system sequence, 3 or 4 values, and you would calculate it. So your output would be, for example, h of 0, that is the 0th value of your h, multiplied by your 0th value of the input. You see now, this is going to take all your sample values and what they're multiplied by in the system, and then you're going to add them up. Right. So this is the best way of trying to do it. You don't have to worry. Having done it, you don't have to worry about where your 0th value is. Not right away. I'll show you what you have to do. you don't have to worry about where to start and where to finish and so on, as you would have to do with the summation. How do you know what your zeroth value is? Of course, your zeroth value is where your x of 0 and your h of 0 intersect, all right? So in this particular case, this here is your zeroth value, so you can write y of 0 is equal to that. However, supposing your zeroth value fell up here, then what would be your zeroth value in the output? So here you're going down, so instead of this being x3, it would be x0. So you'd look and you'd see h0, x0, you'd know that this diagonal carries your zeroth value. And therefore this would be y of 0, then this would be, of course, -1, -2, -3, and so on. And this would be y of 1, y of 2, y of 3. The best thing is to actually do a calculation, which would be easily done on the board. Maybe I can try and do it, not this evening, on the board, and do an example. Right, so that is a convolution table. You can do it using matrices. And here it is simply then you have your matrix of the system response, and X is a column vector of the input signal, and therefore if, for example, your X is looking like this and your H system response, system impulse function, then simply then you're going to just do the math. So you take this and you put it across, you multiply the two matrices, and it will give you your output. So some people like doing it this way here. Notice, of course, that h of 0 would start there, and then these would be zeros, and then so you shift across. Okay. But really the easiest way is to use Matlab. And I'm just being jovial there. Of course, it is the easiest way. So you can just put in your sequence, which is your x, you put in your sequence, which is a, and you just say convolve these two sequences, and it does it for you very quickly, of course. And therefore, at this stage here, you're expected to perhaps do 1 or 2 practice examples, but after that, you are not really going to be expected to do it much further. Therefore, you would just, the idea in this course, of course, is that you're going to be doing signal processing, which you could not do by hand, right? So you're going to be doing it using Matlab. All right, just a few properties of the convolution operation. Commutative property, in other words, it doesn't matter which one comes in what order. So this is a useful property, as we'll see a little later on, that a system here may be consisting of 2 individual systems. You can, if you have one individual system first, followed by another one, then they can commute, right? They're commutative. So you can have H2 of n before H1 of n. So now, the associative property, and they have to be one-sided sequences. In other words, you could do it for a right-sided sequence, or you could do it for a left-sided sequence. But you could not do this if you have both right and left sequences all as one sequence. Right? Remember, right-sided sequence n equal 0 and greater than 0, equal to or greater than 0. Your left-sided, of course, n less than 0. And then finally, distributive property. If you have let's just draw a table by hand. So all right. All right. Right. So in one of either row or column, it doesn't matter. I'll put text here. Not quite what I thought it would be. All right, so I'll put my X across the top, and I'll put text, and I'll put my H. See if we can call. All right, doing Matlab. All right, so let's just take some random numbers. Here, let us say that this is our it looks like we're going to have to put in. What do we put in here? Some values. I put in 3. All right, and we'll do the same thing here again. And text. And let's do, let's see. Oops. Jag vet inte, all right, one more. All right, so I put in, I'm crazy. All right, so let's see if we can I, of course I'm doing the wrong thing. I'm crazy. I've been doing some crazy things all day. All right, so I really want, but I don't know, can I? Can I do it? Can I delete it? Move these out of the way. All right, so I'm going to choose this as my X, and I'm just going to see if I can insert that. All right. I don't know how to get rid of these. Oh, that got rid of it. No? Anyway, that makes sense. Ignore these numbers here. Okay, so here we have our system impulse response. Here we have our input signal. Let us determine that this one here represents x0, and let us say that this one represents h0. So. Right. Okay. So we've put in our values of h, we put in our values of x. So this is a difficult part now. If I ever have this can we? So we have -5, -5. I'll fill in this whole table, and that's 4. And, over there, -9. Oh, yeah. This is very must be a better way of doing this, eh? And we have here -2. And of course, right, only 4 more to go. So, here now we have 9 5s, 45. 45 is -36. Anybody have Matlab up and running on their computer right now? right. Oh, that was easy. Okay. Let's see if I still have anybody. 33 people. Nobody has Matlab up and running yet? All right. So here's our box, rows and columns of multiplications. I hope they're all correct. Nobody corrected me as I went along. So 5 9 is 45. All right. So we will take then a I draw so nice green here. So okay. So our diagonals are like this. That's 1, 2, 3, 4. Oops. All right. So then we can write in here now. We can write y dot n equals. Can you put in some squiggly brackets here? All right. So first term minus 5 is 45 and 4, 49. Next one, minus 36 and minus 9 minus 45 plus 25 is 20. Here's our next one, minus 3 and 81 is 78. Minus 20 would be 58, minus 10 would be 48. Come on. Space. What am I got to know? Minus 2 plus 27 is 25, plus 45 is 70, and 8, 78. So what's that, 18 and 15? 18 and minus 18 is 0, so that's 15. 15, space. And then 10 and minus 6 is 4, comma, space. And finally, minus 4 brackets. This. All right. So our convolution should be minus 5, 49, 20, 48, 78, 15, 4, minus.
Sir, I'm not seeing it get, sir, I'm not seeing it get the minus 5 and the 49.
Right. Well, the minus 5 is a diagonal or with only one value. So you'll notice that the first one has 1, this has 2, this one has 3. Remember, these minus 1 and 9 and 5 and so on, not it's only what is inside.
That one is the
I realize, I see it now, sir.
All right, I realize that
when the power we never see.
I didn't do this column here, but let's just
people will undermine them when they find out this was. And we don't want that.
Yeah, but I forgot this column.
Yes. And we don't want that for. Then we said that our name, but the lady know we said.
Yeah, thanks. Right. The last column here, I omitted, but anyway, we didn't really need this one. So we're not going to count the 15. Yeah. So it
shouldn't the third one be negative 20?
Where's that? Oh, this one here. So it's -9, that's -45. Yes, -20 then.
And the 78, sir, that don't look right.
So, and the 78 don't look right, yeah.
Well, it's supposed to 73.
73. All right, so we just make I think I just write under here. And I'm going to try and edit this because I think it will go all together. So I just put text and I just put which one is it? This should be -20, right? It should be -20, and the 78 should be what? 43? Let me see. No. Oh, yeah.
He said if Congo them probably would already this week.
Sir, it's 78. All right, sir, because that's a -2.
All right. I see what is confusing us here and confusing me too. Is that, so you have -5. I should have. Normally I'd have just written them around the edge, but I just put them here. Anyway, this should be -20. Yes, -45 plus 25 should be -20. So that one should be -20. Maybe I can do this. -20. Let's take it and put it right over there. And then, which was the other one again now? So, 49.
Sir, where you get the 5 again, sir? -5.
All right. We're taking the output here is diagonal, right? So first term is just -5, just this term alone. The second term, 45 plus 4, 49. So that's that term there. The third term, -9 minus 36 is -45, plus 25 is -20. The next term now, -3 plus 81 is 78, -20, 58, -10, 48. So that is right. Then the next term now, -2 plus 27 is 25, plus 45 is 70, and then the 8 is 78. This one is 18 minus 18 is 0 plus 15, 15. 10 minus 6 is 4, and -4. So I think basically all these are correct. I think anyway, nobody tried it out on Matlab?
Not yet, not sir.
Oh. Well, let me go over to my other computer. This laptop I'm on doesn't have Matlab, which is a little stumbling block here.
Sir, I get the first 3 values.
You get the first 3?
Yes, sir.
Well, I wonder if I didn't.
No.
Maybe I did. I'm waiting for my computer to wake up. And with Matlab, it takes a while. So while we're waiting, did anybody try that quiz that I put up?
No, sir. The lab have made it occupied, sir.
The lab, okay. All right. I mean, if you don't have it ready by Friday, I mean, Monday is good. I'll extend it to Monday.
Yes, sir, that would be great.
Oh, all right. So I'll extend it to Monday. All right.
Yes, sir, thank you.
My laptop is up now, so I will put in x equal x again. 5 minus 4, 9, 3, 2, 15. And then h is minus 1, 9, 5 minus 2. Just a moment. I put in the 15. Okay. Right, so I get minus 549, minus 20, 40, 70, 15, 4, and minus 4. Yeah, I got that. So,
So what equation did you use, sir? Oh.
yeah, seeing from my screen here. Don't know if you can. Are you seeing the screen? You seeing anything on your video?
Not very clearly. Not clear.
No, all right. Well, I just put in H first and I put in X. And then, hold on. And that is my, see there, how can I see what my video is sending out? Anyway, well, touch something and lost everything. Oh well, I think I lost everything. All right. Anyway, put in, if you put in the values and then you put in your H, your sequence or H, you can use use a square bracket to put in your sequence, and so you put in your X values. Eh? Not here.
Sir, I did that, but it didn't work. I'm not getting the values that you got or what was on the screen.
You put,
and I put them in the same sequence, starting from.
So you put 5 minus 4, 9, 3, 2.
5 minus 4, 9, 3, 2, and the other one was minus 1, 9, 5, and 2.
Oh.
And the result that I got, if I didn't, as I mentioned, was I got minus 5, 49, minus 20, 68, 62, 51, 16, and 4. And the function that should be used is conv, correct?
Yes.
Okay, yes, and that's the one.
Bracket H, comma X.
Yes, sir. I tried it both ways, and the result was the same. I interchanged the.
Right. Yeah. Yeah, that is the
I'm not sure what I'm doing wrong, because when I work it out as how you had it on the screen before, it is indeed correct based on what is on what was on the diagram.
Right. Maybe you forgot a minus somewhere, or
I'm going to try again, sir.
Right. Anyway. It shows me the difficulty. I have to try. I don't know how better to set it up, but I will try setting up. Maybe I just try a similar example. Try setting it up on the whiteboard, and then I'll be a bit more familiar with it. Okay. Yeah, I should have. I guess you can save it. I seem to have lost everything anyway. Okay. If you if you have a time, I understand everybody tied up with their labs, but you could also try one doing doing it what I call the LTI way. In other words, just
do it along with the way, sir, and then check it.
Yeah, well, I wouldn't really like to try doing with that whole heap of variables or values of the sequence.
Sir, I'm just saying I just don't understand why we're getting different values, and I think we have the same, we input the same thing in Matlab.
Yeah. Read out your X and your H values for me. Let me see again. Okay,
the X values that I have inputted in Matlab are it's 5, -4, 9, 3, and 2.
2, right.
And for the H values, it's -1, 9, 5, and 2.
2 minus, is it -2?
Is it -2? I'm not sure.
Yeah, it all went off the screen. It went off my screen when I tried to move it. I must have touched something and it was clear everything. I think let me try -2.
Yes, sir. I'm going to do that right now. Yes, sir. That was my issue.
Oh, okay. Right. Well, you can imagine if you recorded your voice and you see where you have 40,000 or more samples, and you're going to process them through a system. And I mean, Matlab does it in, I don't know, probably a millionth of a second, a microsecond. And you can see why, I mean, from my point of view, I don't really want a lot of people spending time doing that type of calculation, because you're never going to be doing that in practice, you know. I just want when people, you know, have an idea about convolution and how it works and how to do it. But apart from that, I mean, when I did my DSP exam, yeah, we got a convolution problem to do. But I mean, we did it all right. It's not really hard, but I'm not really interested. I'm basically now more interested in people, you know, learning how to really process signals. So the little 5 or 6 variable numbers, that isn't really important to me. Yeah, all right. Well, we could call it a day for now then. Any
Sir, excuse me.
You're right.
Hello, sir.
Yes, hello. All right, who is?
Sir, how much attempts you're giving us for the practice quiz?
It was probably just one, but I mean, I can open it up.
Yes, sir. That would be great too, sir, because this is a practice quiz.
Yes. All right. Well, I'll open that up, and I will. I also extend the date for the lab till next Monday. Right. So
yes, sir.
Yeah. What about? No, I was going to ask about. There's a problem in the quiz, but like how it seems, a lot of people haven't really done it yet. I won't bother say anything about it.
Okay, sir.
There's a problem, and it actually looks quite hard. I think it's probably about question number 5 or 6. I don't think there are many questions in it. And it gives you a sequence of numbers and it asks you to determine maximum amplitude and so on and so on.
Oh.
Anyway, I'll leave it open. So if after people have tried it, and if a couple of people should be able to get it. I mean, well, maybe mostly everybody. I don't know, but I know these things that when you look at them first, they look difficult and confusing and horrible. If you look and think, and you'll actually see that they're not really that difficult. You know? But I'll give, as I say, because that quiz is actually open, right? It's not.
Yes, sir. But we're just asking for you to extend the attempt to probably 2 or 3.
3, yeah.
Instead of 1.
I'll have to look. Anybody?
The cable people tomorrow.
Sure.
Yeah.
This slide will be up on Moodle or Canvas, or both.
Canvas really, because I think I probably have into Moodle, but I haven't. You see, what happened now is time is against me, you know, and I don't have. Since I'm doing it on Canvas, I just have to keep it up because like Moodle, I'm going to have to learn everything.
All right, okay, sir.
Yeah, so for the moment anyway, I'm setting up I'm staying on Canvas. But yeah.
Sir, so is that it for class then, sir?
Right. It's yeah, I'm really finished. It's only if anybody have any more questions or wanted me to do, well, not really enough time to try another problem. But yeah, only if people had questions.
Sir.
Otherwise, I'm finished till next week.
Yeah, sir.
Yeah.
In the lab, refer to sampling